here today and share with the conference organizers and the audience the topic today, which is about what would be the outcome of surface coating very fine magnetic nanoparticles in terms of the final properties of the system. This is the topic for today. And I would like also to thank all of you online attending this meeting and attending my talk. So here is my agenda for today. Briefly, I will present you the cobalt ferrite nano platform, and then I will switch to a brief description of the synthesis and the surface coating of cobalt ferrite nanoparticles. I will present to you a couple of characterization of this nanomaterial, and then I will switch to the magnetic properties and the influence of the surface coating. And I will finalize my presentation with a key points about the content of this talk. Okay, so let me briefly introduce you to cobalt ferrite nanoplatform. So cobalt ferrite has a standard chemical formula like this on the left-hand side. And this material, it is well known by its high coercive field value. Also, it is well known by the large magnetic moment, large saturation magnetization, and perhaps less well known by its biocompatibility. So, if you look at these three properties of cobalt ferrite nanoparticles, you can move to the applications. The first one is the spintronics, and therefore for using as recording media and also as a permanent magnet. So these three applications, they came from the high coercivity field and the large magnetic moment. In terms of the biocompatibility, you can use cobalt ferrite nanoparticles in the magnetic hyperthermia, which is very interesting application for drug delivery and also for contrast agent for magnetic resonance imaging. So just to emphasize how the biocompatibility of cobalt ferrite has been described, I show you on the lower part of my slide. I can show you the two experiments, actually in vivo experiments, where cobalt ferrite nanoparticles were injected. On the left-hand side, cobalt ferrites were surface coating with citrate, and it was injected in the animal. And then we observe the cobalt ferrite nanoparticles inside the copper cells. You can see the arrow. So the black spots or the dark spot here is a magnetic nanoparticle, cobalt ferrite nanoparticle inside cell, copper cell, in the mouse liver. On the right-hand side, in lower part of my slide, this picture and the arrow, the black arrow, shows actually cobalt ferrite nanoparticles inside a magnetoliposome surface coated with polyethylene glycol. So it was observed inside a capillary, actually. We follow all these experiments to confirm the biocompatibility of cobalt ferrite nanoparticles. So it is indeed a very biocompatible material and ready to be used in bio applications. So how we can synthesize cobalt ferrite nanoparticles. Of course, there are different routes in the literature, but one which is very often used is the chemical co-precipitation in alkaline medium. So how is it? Actually, it's not only used for cobalt ferrite, but can be used for all kinds of ferrites like nickel ferrite, manganese ferrite, uh, and even magnetite. So here, the first step, actually, you mixed a solutions of the metal 2 plus, like cobalt 2 plus, with iron 3 plus. So, and you mixed on the right concentration, and of course in the stoichiometric proportion. And the first step is you heat up the system at about a boiling point, 100 C, and then you drop a basis, like for instance, ammonium hydroxide. So, and then you force precipitation of the, let's say, metal ferrite nanoparticles. In our particular case, is cobalt ferrite nanoparticles. And under this very high peel condition, the as precipitated nanoparticles are actually negatively charged surface. And then the second step is to go to the 0 point of charge to a very low pH by adding nitric acid. So you just end up with magnet nanoparticles, positively charged. And then you can perform a very important step to protect the surface of the as precipitated magnet nanoparticles not to dissolve. And then that means to heat up the low pH precipitation with iron nitrite, iron 3 nitrite, or ferric nitrite, about 100 C for 2 hours. This is a sort of hydrothermal treatment. And this hydrothermal treatment provides you with a system which is actually a core shell. So the core is cobalt ferrite, and the shell a thin layer of magamite. So, and then you end up with the system. So this approach, which is called alkaline co-precipitation, is a standard bottom-up strategy to fabricate nanomaterials. So once it is fabricated, we can go to the second step, which is the surface functionalization of the as precipitated cobalt ferrite. Actually, to find out the best condition for surface functionalization, you should explore the surface functionalization at different pH. So the plot on the upper side exactly shows this. So it shows that surface functionalization with a carboxylic acid group. You can follow by looking at the absorbance of the end material at different pH. We show here pH 2, 5, and 8. And then you can follow the absorption of the asymmetric and symmetric carboxylate group. And it gives you a relative concentration or density or surface gravity of the carboxylic group. And we can find easily that the best pH for surface coating of the magnetic cobalt ferrite nanoparticles is around pH 5. And then we provide the surface functionalization with different molecules in this study. The shortest one was glycine. So we just surface coated with glycine. You can see glycine is amino acid. We use different amino acids and has only 2 carbons in the chain. And actually we perform using 5 different amino acids. So the surface coating was performed with glycine with 2 carbons, alanine 3 carbons, and 4 carbons aminobutanoic acid, and 6 carbons aminoxanoic acid, and finally 12 carbons in the chain aminododecanoic acid. So the surface coating of cobalt ferrite nanoparticles were performed using these 5 different amino acids. So what we learned from this is when we perform a characterization of this material, for instance, the crystal structure and morphology of the end materials. Here, I show you exactly cobalt ferrite, just the core, no surface coating. However, if you perform, if you extract the X-ray diffraction of all samples, they show absolutely the same X-ray diffraction pattern as the core nanoparticles without any coating. That means the coating with different species does not influence, does not change the phase of the core cobalt ferrite nanoparticles core. So if you look at the morphology, for instance, looking at the transmission electron microscopy and high resolution transmission electron microscopy, you can, for the HRTM, you can find the interplane distance characteristic of cobalt ferrite, which is 400 plane, and then the interplane distance is 0.21 nanometer, which is typical of cobalt ferrite. At the same time, from the transmission electron microscopy, we can extract the particle size distribution. On the right-hand side, you can see the histogram. We can fit the histogram like the fitting performed and represented here by the solid red line. So in this particular case was just the core, and the mean size was about 6.7 nanometer, and the size dispersity about 0.42. The fitting was performed using the log normal distribution function. When we perform all the characterization, the morphological characterization, you can see the data or part of the data collected in the table in the lower part of my slide. For instance, the cobalt ferrite, the core, no surface coating, about 5 nanometer in diameter, and coating with 2 carbons, amino acid, glycine, gives about the same size, and aminobutanoic acid, so 5 carbons in the chain, and aminododecanoic acid, 12 carbons in the chain. So the core size doesn't change actually, which means the surface coating process, which is a chemical process, does not change the core morphology of the system. If we turn to the magnetic properties of this material, you can see 2 plots here. On the left-hand side, it's just the hysteresis cycle at 400 K for the cobalt ferrite nanoparticles, just the core. On the right-hand side is the cobalt ferrite for glycine, so 2 carbons in the chain. We can, of course, we can fit the data. You see symbols are, in both plots, symbols are experimental data. And the solid red line is the best fitting of the data using the expression shown in the bottom of my slide. So it is typically the model for a super paramagnetic system. We use the first Langevin function and modulated by the particle size distribution, which is the log normal distribution function. And from this, we can extract, for instance, indirectly the particle size distribution from the hysteresis cycle measurements. So you can see in the inset of both plots, you can see the extracted particle size distribution with a mean size of 5.03 for the core and 5.03 for glycine surface coating. So the data is about the same as the data extracted from the transmission electron microscopy. We can look at the data also for the aminobutanoic surface coating and also for the aminododecanoic, so 12 carbons in the chain on the right-hand side and 5 carbons in the chain on the left-hand side. So again, the solid red line is the best fitting from the data using the super paramagnetic model. And we can extract the particle size distribution and mean size about 5 nanometers, exactly about the same as extracted from the transmission electron microscopy. On the bottom of my slide, I show you the saturation magnetization extracted from this fitting. And that is, remember, 400K measurement. So we can see a systematic variation of the saturation magnetization as you increase the number of carbons in the surface coating moiety. So it goes from 2 carbons at 1403 ml by cubic centimeter up to 1447, slightly increasing, but systematically increasing as you increasing the thickness of the coating. So if you increase the number of carbons in the surface coating moiety, actually you are increasing the thickness of the coating. If you look at the evaluation of the saturation magnetization as a function of temperature from 4K up to 400K, you can see different samples here in this plot. So the upper data is the core cobalt ferrite nanoparticles. The green one, the second one, is the surface coating with 2 carbon chain with glycine. And the third one is the blue one is surface coating with the amino acid containing 5 carbons in the chain, aminobutanoic acid actually. And the lowest one is surface coating with a aminododecanoic acid, which is a moiety with 12 carbons in the chain, meaning is the thicker thickness, is a thicker layer on top of the cobalt ferrite nanoparticles. So the solid lines here are the best fitting of the data using the block type law, which is the ratio between the saturation magnetization over the saturation magnetization near to 0K. It follows this expression, and then we can extract not only the saturation magnetization at the lowest possible temperature, but also we can extract the B and beta parameter. And it's very interesting if you look at the table in the lower part of my slide. So the last column is the beta coefficient. It's about the same. It doesn't change as you change the surface coating. Of course, the B value, it changes, but the saturation magnetization at 0K also changes systematically as you go from 2 carbon surface coating up to 12 carbon surface coating. So this systematic variation, it's a very important way to modulate the magnetic properties of a small size magnetic nanoparticles like 5 nanometers in diameter. So we can modulate the properties of this material just modulating the thickness of the surface coating. And this is a very interesting way to modulate magnetic properties. So now we want to step further to try to understand the data. So when we try to understand why the magnetic properties change monotonically when you change the thickness of the surface coating, we need to look at particle-particle interaction, actually. So in the particle-particle interaction approach, you have 2 important contributions. One is the exchange interaction between neighboring nanoparticles. But exchange interaction is typically a very short range to a very short distance, regardless the coating thickness. On the other hand, the second very important contribution to the magnetic properties and also inside the particle-particle interaction model picture is dipole-dipole magnetic interaction, which is a long range. And this one, of course, depends on the thickness of the coating. So this one is the coating dependent property. So modulation, actually modulation of the magnetic properties of very teeny magnetic nanostructure by changing the surface coating actually is dominated by dipole-dipole interaction. So let me summarize some important points about this talk. The first point is that very successful way to synthesize core shell cobalt ferrite nanoparticles is a way that preserve the core, and that is performed by the alkaline co-precipitation of cobalt 2 plus ions and iron 3 plus ions, following the mild hydrothermal treatment with ferric nitride. So that provides a core shell and a very thin shell of magmite, the magmite phase that preserves the core cobalt ferrite phase core to be chemically changed. The second point is we come out from this study is that this shell thickness actually can modulate the physical properties, in particular the magnetic properties of very teeny magnetic nanoparticles. So the third point is that if you look at the hysteresis curve of this very teeny cobalt ferrite, around 5 nanometers in diameter, they all exhale superparamagnetism at 400 K. However, if you go to lower temperature, so then you have the hysteresis, you open the hysteresis cycle, and then you will find the magnetization of this 5 nanometers cobalt ferrite nanoparticles does not saturate, even below 100 K, even if you apply a very strong field of 3 Tesla. And finally, the properties that responds for the modulation of the magnet nanoparticles by modulating the surface thickness is the strong particle-particle interaction. And particularly important is the dipole-dipole interaction. So I wish to finalize my presentation once again. Thanks for the organizers of this meeting. It was my honor to be here today and be invited for this talk. And also, I would like to thank all of you attending this meeting and attending my talk. If you have any further question, you can contact me by my email address, which is on the bottom of my slide. And thanks again. Thanks, Ms. Chair, for the introduction. And thanks
Thank you very much, Professor Paula, for that informative sharing. All right, let's see if there's any question from the floor.